Hello everybody, I'm here to show you an example of rectilinear motion problem related to uniformly accelerated motion, in other words, constant acceleration. So here we have two cars, car A and car B, with the given initial velocity of car A is 30 miles per hour, and we have to do a conversion in a minute. And let's say the driver of car A is pressing on the gas pedal and accelerating at the rate of 2 feet per second square, and this is a constant acceleration. Now, car B is 96 feet ahead of car A, okay? So this is 96 feet ahead of car A. And at the given instant shown, car B has a velocity of 45 miles per hour, but the driver in car B is actually pressing the brakes and is decelerating at a constant rate of 1.5 feet per second squared. So the question is, we want to find the time at which car A will reach car B. So how do we go about finding the time? And eventually we can also find the position when they reach, at a certain point. And actually that's how we're going to actually approach this problem. Remember, for constant acceleration problem, you saw in another video that if A is constant, we have a bunch of equations that we can use. Of course, we can go through the definition of acceleration and velocity and integrate and get these equations. But we already have determined these equations, such as V equal V0 plus AT, or S equal S0 plus V0t plus 1/2 AT squared. Of course, this is only for constant acceleration or uniformly accelerated motion. And then, of course, there is also another useful equation, V squared minus V0 squared equal 2A S minus S0. So which equation is going to apply to our case here? So look, when car A gets to car B, they're going to be at the same position. So let's say this is car A now, and this is car B. So actually, the position of A relative to a reference is going to be SA. Let's pick this to be our reference, for example. And here's car B, and car B is going to have position SB with respect to the same reference. So in order to solve this problem, we have to set SA equal to SB. And that's how we're going to solve for time. And the equation that you want to use clearly is this second equation right here. Of course, we have to do some conversions here, right? And that's very easy. Remember, 1 mile is 5,280 feet, and 1 hour is 3,600 seconds. So you could multiply by 5,280 and divide by 3,600 seconds. But let me show you something interesting. It turns out that every 15 miles per hour, and this could be used in other problems, every 15 miles per hour is 22 feet per second. So if your velocity is a multiple of 15, like 30 is what? 2 times 15. So initial velocity of A, V0A, is going to be 2 times 22, 44 feet per second. And similarly, initial velocity of B, V0B, this is 45. What is 45? 45 is 3 times 15, right? So it would be 3 times 22. So that would be 66 feet per second. So that's a quick way to do the conversion. Of course, it has to be a multiple of 15. Otherwise, if it's not a multiple of 15, you just use the conversion, the usual conversion. Okay. So let's go ahead and establish the equations in terms of position. So let's start with S sub A. So initial position is 0 because we are at the reference. Initial velocity of A, we just did the conversion, is 44 times t, right? Plus 1/2 acceleration of A is 2 t squared. So if I clean this up, which is not much cleaning up, so 44t plus half of 2 becomes t squared. So that's S sub A. Let's do it for S sub B. So initial position is what? 96, right? Because it's 96 feet ahead of car A, right? Plus initial velocity of B is 66 feet per second. And this guy, remember, is decelerating at the rate of 1.5, so it's a negative. So if we clean this up a little bit, it's 96 plus 66t minus 0.75 t squared. So remember, now what we have to do is to set S sub A equal to S sub B. And I'm going to do that on the next page, and then we go ahead and we end up having a quadratic equation that we can solve. So let's go to the next page. So SA equal SB, right? So SA was t squared plus 44t, and SB was 96 plus 66t minus 0.75 t squared. So if we bring all the terms to one side, let's say we get 1.75 t squared, right? Minus 22t minus 96 equals 0. A quadratic equation use the quadratic formula. So this is A, this is B, and this is C, right? So t equal minus B, so that's positive 22 plus and minus square root of minus B squared plus or minus 4AC, sorry, minus 4A times C, which actually happens to be a positive outcome, divided by 2A. All right, if you work this out, I believe we end up getting a 34 in the radical, coming out of the radical, and we have a 3.5 here. We're going to get two answers. One is going to be positive, one is going to be negative. Of course, we cannot accept the negative. So if you go with the positive one, you end up getting a 56 over 3.5, which I believe is 16. So it takes 16 seconds for car A to get to car B. So this is car A. Remember, this is car B. But at some point, car A and car B are going to be at the same position. And we can actually calculate that position. Doesn't matter, you could use either SA or SB. So if you say SA, which is equal to SB, equal to, let's just use the t squared plus 44t. Notice that we have a 16 squared plus 44 times 16. I believe that becomes 960 feet. So this would be the 960 feet. Of course, this is not to scale. In other words, if you want it to be to scale, you have to put more like B should be here, because this is 96 feet, remember. Okay, so took 16 seconds for car A to get to car B. And this was a very simple example of constant acceleration or uniformly accelerated motion, rectilinear motion, for which we were able to use these formulas that you saw in another video how they were developed. Okay, as always, thank you for watching and listening.